We were in the middle of talking about page replacement. Anyone remind me what page replacement? What's page replacement? Yeah. Salience? I should say it's memory. From where to where? Replacing the virtual. Yeah, where is the virtual held? Hard drive. In the hard drive, right. So page replacement is bringing a page from the hard drive into memory, exactly. So we're now talking about using a stack to do the most recently used page reference. In other words, we want to keep track of the page. The most worthwhile page to remove is the least recently used page. If we haven't used it in a long time, it's probably worth taking it out if we have to choose somebody new. So for example, if this is our situation, we're at A and we're about to get to B, we're about to have 7, but we've had all of these. So our stack would look like this. We would make a stack here. This is the idea of using a stack to represent it. 2, 1, and then 0. And then if you go further back, 7, and if you go way back, 4. So the oldest thing in the stack. So when if we come here, we say we want to use 7, so we're going to have to change our stack to keep track of the fact that it's now recently used. So we're going to take the 7 from here and move him in the stack. You never really saw a stack like this because usually the stack you just popped off the top one. Here is a stack where we're shuffling it. We're taking something and we're taking somebody out and we're always putting him at the top because he's the most recent one.
You're able to do that?
And, yeah, you can do anything. You can make a stack and, that works any way you want. Yeah. It's programming. It's just a matter of programming. It's a simple matter of programming. Now, if we would have to get rid of somebody, who would we get rid of? If we had, let's say all of a sudden, so we only had 5 spaces, and all of a sudden, a new page comes in, number 9.
Yeah, 9. Then we'd pop 4.
We'd pop 4
because it's the least.
Right. So it's a kind of weird stack where it's the lowest one gets popped. Usually you pop from the top and push.
It's like a priority queue.
Exactly. It's a queue. It's a kind of a queue. But the point is we're going to pop out 4. Yeah. He is the worst one. So we have a pointer to tail, pointer to head. And whenever we scan it, we find somebody, we're going to move him up to the top to be the head. So that would be a way of implementing keeping track. Of course, we can't really do that in, we wouldn't want to do that every time there's a page reference because if every time there's a load in our program, it could be every other line of our code. We're going to start moving around pointers, going to slow it down by a factor of, 5.
You're going through its inefficiency for every time.
Exactly.
You go through and find it and where it was.
And then move things around every time for a page reference. That's insane. Mm-hmm. But it could be done. Maybe you could have special hardware that automatically did it. That would be fast, but still it's kind of it's a solution that works, but it's not a good solution. Mm-hmm. But this solution is based on the idea of actually knowing which is the least recently used. We're going to do another idea, which is what's called an approximation of the least recently used. Now, we're not going to actually know who's the least recently used, but we'll have, welcome Shai. We'll have an idea of which is the least recently used. So in other words, it's an approximation. So what do? We're having different, first of all, we're going to have special hardware. It'll still be slow, but it'll still be somewhat slow, but it won't be so slow because we'll have hardware especially for it. I'm not sure why I wrote still slow. It's still slow, but certainly not as slow as the other. Reference bit. With each page, associate a bit initially set to 0. When a page is referenced, set it to 1. Okay? Did we talk about that? We didn't talk about this, no? Did we talk about this? No, I don't think so.
I don't think so.
So you guys should be excited to learn something new.
I'm so excited.
When the page is referenced, you set the bit to 1. So you have a bit by every page that's in, and whenever it's referenced, you set the bit to 1. Replace any with reference bit 0 if 1 exists. Replace any with right. If the bit is set to 0,
then it means he hasn't really been referenced probably. And so we'll remove him. But we'll remove anyone who has a 0. So it's not the least recently used. What is it really? It's really
Any
like,
that haven't been referenced.
it's really the set of things that have been recently used less recently than others.
Yeah.
Like we divide the world in half. There's those that have been somewhat recently used and those that have not been somewhat recently used. Anybody with a 0. Now, we do not know the order, however. We don't know the exact order. That's the basic idea. Of course, exactly how to do it, exactly how to do this, we'll see, because what about this? What about this problem? Let's say somebody gets set to 1 because he's referenced, and somebody else gets set to 1. Eventually, they'll all be set to 1. Eventually, everybody will be set to 1. So, because everyone's referenced at some point. So then how will I choose who to remove? Nobody will be 0. So we have to have a way of like, in Hebrew, you say apes. So you have to a way to do 0 to calibrate.
Yeah.
That's what it means. Apes from the word ephes, from the word 0. Set to apes. You're right.
It's on the 0.
It means set to 0. Literally, it means set to 0, and that's what I mean.
Well, that's what it's called in Gun, isn't it?
Yeah.
You're zeroing it.
Zeroing it out. Yeah.
What's the thing on a scale?
Yeah. When you can put on an electronic scale, you can put like a bowl and then press the 0 out button, and now it's weighing from where it is, even though it has a bowl on it. And now you put things in the bowl, and you can weigh what's in the bowl and not the bowl itself because you've zeroed it out. So that's the word in Hebrew is apes. We're gonna have to somehow set the 1s back to 0 at some point. So we're gonna use something called the second chance algorithm, which is another important algorithm that you should know for the course. Second chance algorithm, generally it's a FIFO plus hardware provided reference bit. That's what we said. So it's a FIFO, first in, first out, but we'll see. It's also called clock replacement. I'm not sure exactly why it's clock replacement, but it uses like a clock, kind of you're counting. I don't know, whatever. I don't know why it's called clock. Here's the basic idea. If page to be replaced has a reference bit 0, replace it. If its reference bit is 1, then set it to 0, change it to 0, but leave the page in memory, replace the next page subject to the same rules. So let's do an example. That's the basic idea without explaining too much, because we'll see an example. An example explains it better than the words. So let's say we're at this is not home later called. Resume recording. Okay, so back to this example. Here is our reference bits. These are the pages that they're referring to. So it says here that this page hasn't been or whatever reason it's 0. We'll see what the reason is. But let's just say for whatever reason it's 0. The next page, the next victim comes in. Sorry, our pointer is currently pointing to this one. And we'll see that the pointer is gonna go in a circle. The arrow should really be over here. We're gonna go around in these reference bits in a circular way. And it's like this. Let's say we want to choose a page to remove from memory because we have no more space and we have to take somebody out to bring the new page in for this program. So we are at here, we can't kick this guy out because it's a 1. We can't, so we'll move on to the next one. We can't kick him out, but before we move out, we're gonna change this 1 to a 0. Because why? Because if they're all 1s, and we come around again, eventually we wanna hit a 0. We wanna guarantee that we'll eventually find a 0. So we're gonna set this guy to 0 because we don't know, maybe we're never gonna find a 0. So we'll set him to 0. Now we go to this guy, he's also a 1. What are we gonna do? We're gonna skip him and set him to 0. So this will be a 0 now. Now we come to this one. Oh, we got lucky. Here's a 0. This will be our victim. So that's what it says over here, that our victim is now this page, and these two have been changed to 0. This 1 and this 1 have still 1s. Now, next time I come around, I will immediately go to I'll skip this one. So this is our victim. We've selected her. The real question that's not explained here is what happens when someone comes in. And in other words, a new page comes in. So we put him here, right? Do we set this to 1 or to 0? First of all, we're going to move this is our victim. We're going to put him here in this page, in this place, and we're going to move the pointer to the next guy. So next guy, we're going to start here. But what number do we give him, 0 or 1? So actually, there was a problem on an exam last year, where where the people were claiming that their teacher told them they put a 1 there, and some people were saying, no, their teacher told them a 0 there. The truth is, it doesn't really matter, because, I mean, you could put a 1 there, in case you're saying it's because it's being referenced now. So it should be 1. I'm referencing this page. That's why I brought it in. So it's sort of logical that it would be 1. But I could put it as a 0 there, because anyway, I'm not going to select him next time, because I've already moved the pointer. And by the time I get all the way back to him again, well, if everybody is 1 and he's 0, so, well, in other words, the way it works like this. Usually you have hundreds of references, and 1 out of 100 or 1 out of 1,000 is to a page that's not in memory. It's not like you're going to constantly bringing in new pages. So in a normal case, I'll move down to here and I'll be pointing here. Even if this is a 0, now I'm here and I don't need a victim because I have many, many references. And in that time, this 0 gets changed to a 1 because I referenced it. This 0 gets changed to a 1 because I referenced it. And maybe this 0, if it was a 0, will be changed to a 1 also because I reference it again. I'm probably going to reference it many times. And then finally, I reference a page that's not in memory. So I'm over here and I see it's a 1. So I'm going to skip and change to 0. See, it's a 1, skip it to 0. A 1, skip it to 0. But this one I never referenced since the last time I had a victim. So he's a 0. Right? So it doesn't really matter if this is a 1 or a 0. Either way, it would work. In other words, it's implementation dependent. You could do the same algorithm could work either way, is what I'm saying. You could work, it would be called the same algorithm. It wouldn't be called a different algorithm just because I had this as a 1 or a 0. So it's actually, the truth is the question wasn't about that in the exam. It wasn't about is this a 1 or a 0. It was like they used that as a way to answer another question. I think it was a kind of not important point. But in any case, you can say this as a 1 or as a 0. Either way, no, it has to be set. It has to be set to something. What?
Basically, doesn't matter.
It doesn't matter for the algorithm in general. No, it doesn't matter for the algorithm in general. You understand why? Because, in other words, these zeros, it's not like if let's say these were all 1s, and I was pointed here. And they were all 1s and I was pointed here. I went through all of them, and I came all the way back, set them all to 0s, and we're all the way back to the top now, and he's a 0, so he'll be my victim. Now, when the next page fault comes, here's a great question exam. When the next page fault comes, will this be the page that I replace? It's a 0 after all. Remember, I went through them, but they were all 1s. I changed them all to 0s, and I came all the way back to the top, and I chose this guy as my victim. And next time there's a page fault, will this guy be the next page? Will this guy be the victim for sure? What?
Yes.
Yes, you say. What do you say, Shai? You don't know. You should take a stand. What do you say?
I say it will be.
You say it will also be.
No,
Okay.
I say it will not.
Will not. Okay. Why? No, take it. No. But why? Why do you say not?
I think that it depends on the implementation of the 0 or the 1, and we start from the beginning again.
No. We're definitely starting. We're definitely going back here, and they're all 0s. They're all 0s. When you got up here, we set them all to 0s, and now I'm pointing to this one. He'll be my replacement, and now I'm pointing to this one, and he was a 0. But the point is like this. So I'm saying again, they're all 1s. I set them all to 0s, and I came back and I replaced this guy. So the next victim, the next page that I need to replace is not necessarily going to be on the next read, the next load word. It could be that I'll have 100 load words, and all the time I'll be hitting pages that are in memory. And in the course of those 100 load words, all of those 0s will get set to 1s again. So it could actually be that this guy will be the victim again. It could be this one, and it could be any, we don't know. We have no way of knowing who the next victim is going to be. It depends on when the next victim is. If the next read is a victim, if the next read requires me to select a victim, then it will be this guy. But if it's who says the next read, maybe it's going to be in 100 reads from now. And in 100 reads, in the meantime, a lot of those 0s get set back to 1 because they were referenced. That's the reference bit. That's the key point to understand here. We're constantly wiping them to 0. But then as they get referenced, so who will end up replacing? Somebody who wasn't referenced since the last time we had to replace a page. It's kind of like that. So you could actually invent another algorithm, which would, after you selected a page, automatically set them all to 0. You could do that. You could set everybody to 0. And then
What's wrong with the the singular, most recently used. So everything else was not used, only one was the last to be done.
He could also be set to 0. And then I'll just wait for the next victim. And in the time until I need to choose a victim, I'll see who was referenced, and all those ones are referenced, I'll skip them. You see what I'm saying? It would be a similar algorithm. It wouldn't be quite as perfect as this. It wouldn't be as good as this, but it would be also working. Anyway, the point is, it's called a second chance. Why second chance? Because if I was pointing to you, I wanted you to be the victim, because you have a 1, I'm going to give you a second chance for life, but not a third chance. I'm going to lower it to 0. And if I hit you again and you haven't been accessed since the last time, then you'll be the victim. So I'm giving you a second chance. But if in the time you've been referenced again, oh, your second chance brought you back to life. Now you're 1 again. And now you could again get a second chance. Yeah.
So, question. So if you bring something into memory and you have the reference bit as a 0, then it only has 1 chance. Because the next time it comes by, you'll get rid of it if it's still a 0. But if it's a 1, then it'll have 2 chances.
Yes.
So it'll take 2 rotations.
You're right. So logically, therefore, you're concluding that it should be set to 1.
Yeah. So it has
To get now that it came in,
or
it could be set.
Or it should be set to 0 so that it doesn't take up memory if it's not needed.
In other words, maybe if it says don't give it 2 chances just because we just brought it in, if we haven't referenced it in a long time, we went through the whole cycle and everybody else
never been referenced, and why keep it?
Why keep it? Or again, it does. I agree with you. It does make more sense. The way I taught it for 10 years is that it gets a 1 in it, and then I heard that some other teachers taught it that it gets a 0.
Yeah, I remember from last week I mentioned that I said that maybe it's brought in as a 0, then it's referenced, so it's given a 1.
Well, it's referenced when it's brought in. It's because it was referenced.
No, but I think the first is put into memory, and then it takes it from the memory.
Oh, you said
So then
we
it's a
talked
0.
about this. What were we talking last week or not last?
Yeah, last week.
We did this slide.
I think so. I it's vaguely remember. I remember mentioning this.
Okay. So in other words, you're saying we bring it in and then we restart the command, and then when we restart the command, we now reference it and find it, and so it'll get a 1.
It's like the command is waiting for it to be there, and then it keeps
At the moment we bring it in, it's a 0, but then we have to rerun the load word, and the load word will now cause a reference. Okay. Keep a counter of the number of reference bits that have been made for each page. Not count. We have a counter, how the number of references that have been made to each page. Just and then you have we did talk about this. Yeah, I think
there's multiple chances.
Okay, we did. That would give it no. The idea here is keep a counter of the references that have been made to each page. It means we would just say a page that's been, let's say, referenced 1,000 times. He's an important page. So don't get rid of him. Another page will be referenced 500 times. You could get rid of him. It's only 500 times. So that would be. And then we said the problem with that method is that it would, if somebody who's referenced 1 million times but hasn't been referenced for a long time would never get out of the system, because he has a lot of merits in his bag, but he hasn't had a recent merit, so he really shouldn't. So then we have least frequently used. Replace the page with the smallest count, right? That's what I said. There's 500. Or you could replace the most recently used with the largest count, like on the theory that has been in there so long, he's probably not referenced anymore. He's got a large number. He must, in order to accumulate such a large number, he must be in there a long time. So let's get rid of it. Okay. Now allocation of frames. Each process needs a minimum number of frames. The IBM 370 has six pages to handle SS move. They have certain instruction that requires the instruction is 6 bytes and may span 2 pages. The instruction itself, one instruction could actually expand. It could actually be 6 bytes long, and therefore be 2 pages. And then it has a from handle and a to handle. Where are you copying from and where are you copying to? These are each also long things. And they could expand. They could be over 2 pages. So that could be possibly 6 bytes. So that's just saying that one single command theoretically could require 3 pages, 1 line of code. Maximum, of course, is total frames in the system. The maximum, the minimum is whatever I decide, based on the program. The maximum is the whole system. 2 major allocation schemes: fixed allocation and priority allocation. In other words, one would be fixed, where I would give everybody 5 frames when they, that's it. Another one would be priority. Now, some processes get 10 frames of memory, some processes get 5 frames. There are many variations. Fixed allocations. Equal allocations. For example, if there are 100 frames in a computer and there are 5 processes, give every process 20 frames. You might want to keep some free frames. You might keep some as free frame pool, buffer pool. We might keep some extra frames in case somebody needs an extra frame. We'll have an extra frames. Proportional allocation. Allocated according to the size of the process. You can say this process, the program itself is 100 megabytes. So I'll give him more than I would give to another program that's only 10 megabytes. And it's because he actually is bigger. You're probably going to need more frames. Dynamic is degree of multi-programming process. You can also have dynamic, which is to say that as the process size changes, or as more processes come into the system, I might give less memory to each one. I might constantly change the amount of memory given, which is an interesting idea. In other words, let's say I have 100 processes. I have 100 frames and 10 processes. So each process I'll give 10 at first. Now all of a sudden another 10 processes come. So now I have 20 processes. I'll reduce the amount that I give to each one by 5. So now everybody's going to have to get by on fewer frames. They have to do a lot more page replacement, right? We saw that this IBM program, which has that command, might need a minimum of 3, but as long as they don't reduce it lower than 3, then he'll be able to get by. In other words, the idea is we can have a dynamic degree of, dynamic amount of allocation, which is based on the multi-programming level. How many multiple programs are running at the same time? What's priority allocation? Use a priority allocation scheme using priority rather than size. If a process P generates a page fault, select the replacement. Select for replacement one of its frames. Select for replacement a frame from a process with lower priority. Now, you could replace its own frame, right, from itself. You can say, oh, you need a new frame, so you have to lose one. Or you can say, no, take it from another process with a lower priority. This process has 10 and you have 10. All of a sudden, you're a high priority process, you need 11th page. We'll take it from the other guy. And he'll only have 9. Okay, thrashing. So thrashing is a concept in operating systems, which is if a process doesn't have enough pages, then the page fault rate is very high. In other words, if I start having multiple programs and I reduce the amount of frames that I give to each process to the point where the process has very few pages, what's going to happen? Every time there's a page reference, maybe every time he needs a new page. And it could be that like he needs page A and B, but we only give him 1 page. So he'll swap out B and then bring in A, but then he's any B. Swap out A, if B, bring in A. He's going to go going back and forth. I need A and B. So, but we only give you 1, so you can't get anything done. So all the time the operating system is going to notice, oh, I need to bring in another page, so it's going to do a swap. So instead of getting any work done, I'm just thrashing about. That's what it means, thrashing. When a squid is or not a squid, a eel is thrashing in the water, he's not making any progress. He's just thrashing around, he's not getting anywhere. So that's the idea of thrashing. Because I'm swapping pages in and out, I'm not getting any real work done. So page fault we have a page fault to get the page. Replace the existing frame, but quickly need to replace their frame back. In other words, we need to bring that one that we just got out, we need to bring it back. This leads to low CPU utilization because the CPU is trying to get to do the next command, but it can't until the page has been brought in. So the CPU is sort of idle, but the disk is busy, right? You have a situation where the disk is just running, and your CPU has just nothing to do, waiting for the page to come. I mean, the worst situation would be where you had a command that needed 2 pages. So a single command, and I only had 1, and I kept bringing out, I'd never get anywhere. Operating system thinking that it needs to increase the degree of multi-programming. Oh, so now since the CPU utilization is low, the operating system may say, oh, the CPU is not being used because the I/O device is constantly bringing in things from the hard drive into memory and moving them back. And the CPU is just waiting around all the time. So it must be the CPU is idle. So let's put in more processes into the computer. Let's take a process that was had been delayed and had been put on the disk, had been swapped out, and let's swap it in because the CPU is idle. But now that process is going to require memory, and it's going to cause more swapping. It's going to cause more swapping and more thrashing. So this is like there's if our indicator for when to increase multiprogramming was how busy the CPU was, then we're going to get a false alert here. We're going to think that the CPU is available when he is available, but there's another reason why we can't get anything done, because the disk is constantly running. Thrashing, a process is busy swapping pages in and out. Okay. So here we have this little graph. Let's see if we can understand this graph. Degree of multiprogramming, CPU utilization. So the idea is like this. If I just have one, this is like I have one process. So the CPU is utilized at a low level. As I increase the number of processes that I run at the same time, the CPU is going to be used more. Because like most processes, let's say a process is got I/O and CPU time, but the I/O could be very slow. So I have only two processes. They could both be at I/O and the CPU is just totally waiting. So I add another process and another process. I keep adding and I get better utilization until a certain point where the CPU utilization, as I increase, it actually goes down. I get worse utilization. In other words, I add another process. At this point, I add two more processes, and all of a sudden, the CPU utilization goes way down. Because I've got, why? How could that be? It's illogical. No, it could happen because of thrashing, because the processes are busy waiting to bring in and bring out things from the disk, and so the CPU utilization goes down. So we have to deal with thrashing, and we have to solve that problem. And the way to solve the problem is by giving every process the amount of space it needs. What is it? Lebensraum. Yeah, we need to give every process Lebensraum. We need to give them enough. What?
Living space.
Living space, exactly. Why does demand paging work? Well, so what? I like to use unusual references. What?
Got that reference.
Why does demand paging work? So, in other words, what I mean by that is like, why don't we always have thrashing? The answer is because usually processes use, even though their spaces are very large, they usually use a certain number of pages that are near each other. And even if the program moves on to the next stage of the program, then it's using those pages in that area. It's like if it says it's doing a set of functions over here, and now it's doing a different type of procedure, so it's a fun set of functions over here. And then it moves on to a separate section. So there's what's called locality or locality model. What is local to you? What is your local area? It's like if you think about if a person lives in a certain neighborhood, most of his time he spends in the neighborhood. Once in a while he goes to the ice skating rink on the other side of town. But most of the time he goes to shopping. You know, that's why there's a barber shop in his neighborhood. There's a barber shop. He doesn't go to the other neighborhood's barber shop. He goes there unless he used to live there. But he stays in his neighborhood. He does his shopping, his barber shop, his hardware store. He doesn't go far away for those things. Occasionally he goes far away. So that's the idea of locality. Same thing with a program. A program mostly is using this area of memory, and it may eventually move. It may, change its residence to be in a new neighborhood, and now it'll use those things. So that's the idea of locality model. Process migrates from one locality to another. Localities may overlap, which is that I may not go from here to here. I may go from here and then still use some of the previous one. So why does thrashing occur? So we can say this nicely, the sum of the size of all the localities of all the processes is larger than the total memory, right? If I can't give you your locality, if I have 10 processes and I can give each of them I can put in memory their whole locality, then I'm fine. If every process I can get its full locality into memory, but if I can't, if your locality, I can't get into memory and also get everybody else's locality in, then I'm going to have a situation where you're constantly needing these pages and there's no place for you to put them. So if the sum of the locality of all the processes is larger Now, that's not the sum of their whole program. Some of their locality is larger than the total memory size of the computer, then I will probably have thrashing. So we can limit the effects of thrashing or limit thrashing by using locality or priority page replacement. So the idea is that we're going to we're not going to prevent that. If we have actually the size of locality is actually too big, then we're going to probably have thrashing. But our goal now is going to be to figure out the locality of a program and not give it more than it needs, so that we'll have enough memory for everybody. Notice, why could I have a problem? Let's say the sum of the locality is not too big, but I gave this guy to this process way too much. So now I don't have room. Even though I theoretically could arrange all the data in the right way, I didn't arrange it properly. I gave everybody 10, but because I gave everybody 10, some guys only needed 5. And this guy needs 12. So now 12, the guy who needs 12 will be in a thrashing situation, and it'll cause the whole system to be thrashing.
How does priority page replacement?
What, say it again? How does what?
How does priority help with that? Kind of just picks on the weak guys, the weak processes.
Yeah, I guess the process that needs less pages, we'll take his pages away. We won't give him pages.
So it's thrashing. Just
no, he doesn't support thrashing. No, because we take away from the guy who had 5, we reduce it to 10 because that's all he needs. We'll now have 5 free pages to give to the higher priority process. Why is he high? It's not really higher priority, but we decide his priority is based on his needs. It's like communism. What does communism say? From you know what the main line of communism is?
Everyone what he needs.
No, from each according to his ability, to each according to his needs. So we take.
Love the random ideas of like all these.
Yeah, these are.
the computer is basically World War II.
Yeah.
Everyone's like, oh, he's the weak one. Let's take up his territory. Let's bring over there.
You're just trying to quote from Lenin, actually. That I thought was a famous quote. I thought a famous idea. I didn't realize it was from Lenin, but I forget now what it was. Okay,
All the good things.
Stalin had a lot of good things. Stalin, Stalin's one of his famous, 2 famous statements that I know of Stalin. One is what? Stalin was when they said, "Well, how can you do this revolution? You're killing so many people. Even if you're going to do something good, you kill so many people." He says, "Well, you have to break eggs to make an omelet."
Yeah.
That was his.
That
That was one of he coined that expression.
and you're like, that's a good thing.
And no, I'm not giving any opinion. Forbidden for me. I'm an educator. I do not give opinions.
Yeah.
And the other,
Politicize that.
yeah, no political stance. I assume
You could be against.
I'm pretty much against Stalin. Yeah, pretty much. I think he killed a lot of people.
Politicize.
Pretty much.
It's some good things. Gave us that phrase.
Give us what?
Gave us that phrase.
Yeah. Another phrase he gave was that people said that the Russian army is a low quality army. They don't have a fight. The people are not trained properly. They have good equipment. You're building a lot of tanks. It's true. In World War II, I mean, the Israeli tanks are nothing compared to what they had in World War II. They like before Stalin started the whole building, because before the Germans attacked, they had like 10,000 tanks. 10,000 tanks they had, something like that. That's the number I remember. And the Germans wiped them all out. But then they had to build more. But so Stalin said it's true, our quality is not so great, the quality of our equipment and our soldiers. But quantity is a type of quality. Quantity itself is a type of quality.
That's true.
That's what he said.
That's true.
If you just have enough quantity, even if it's not such great stuff, you'll eventually win. That's actually how the Americans beat the Germans, because they had better tanks pretty much than we did, but we had more of them, and our tanks. It's not like they couldn't kill a Panzer; they could, but they had to hit it from the side. It had to be a certain range, so they would hide behind trees and things, and they would try to, and they would drive them out. But the tanks, objectively, the German tanks were better.
Good American tank movie is Fury.
But they were fast.
That was the
American tanks were what?
World War II American tanks.
Yeah.
Movie Fury. It's awesome.
Oh, isn't that the one of Fury? Isn't that the one about the Jewish, but also about like a band of Jews?
It's about a tank crew.
Oh, that's-
Glorious bastards.
Yeah.
No, this one's about a tank crew going through like rural Germany.
I don't know if I saw it. I know that they would put like, they would cover their whole tanks with like sandbags and stuff.
But we still do that.
Because they would get blown up otherwise, like they knew that their armor was not good.
Do that in Israel too.
They do that in Israel too? That's pretty bad if you have to do that. But okay, what is this beautiful? This is a beautiful picture. I want everybody to like have a copy of this on their wall in their house. It says like abstract art.
Oh, yeah, for sure.
What is this a picture of though? It's actually execution time. What this is execution time. It's going like this. So this is as we're going, and this is memory address page numbers. So this is page 18, 19, 20, 21, 22, 24, 26, 20. These are the page numbers. And this is execution. And what it's saying is like this. In the beginning of this execution of this same program, most of, look what we see here. We see that the page references are over here in page 24, 25, on this whole area. And then at a certain point, look, it drops. And we lose page 25 or whatever that is, 23. 23 goes out. But we gain, but over here we before had like 30, but we didn't have 31 and whatever. We didn't have 33 or whatever that number is. But now we do get it. Now we get this stuff. Now we're over here and less over here. And then at a certain point, we're way over, we're actually are using this part of the program and not this part at all. So what the picture just to show you that locality changes over time.
There's overlaps there.
They're over, yeah, it's not exactly right. It's not like you immediately jump to a new section. Usually you migrate. Okay, so we're going to learn something called the working set model, which is not to be confused with what we already learned, which is the second chance model. That was for page replacement in general. This is the working set. So here what we say is like this. Delta is the working set window. It's a little bit confusing here. So the working set window, a fixed number of page references in the past that we will examine to determine how many frames of memory this process should be allocated. So the working set window is how much we'll look in the past, because let's say we had 1,000 page references in the past minute. In those 1,000 page references, which pages are referenced? Page 1, 2, and 3. If we would go back further than 1,000, maybe we would see that page 4 was also referenced. But we're not going to look that far back. We're going to set up a window. And that window is we always look back 10,000 references, let's say. And in that time, whatever pages were referenced in that window, we'll call it our working set. In other words, the set of pages that we should have in memory. Because we've used them in the past 10,000 references. Right? In the past 10,000 references those pages. Theoretically, we should examine these old references at every clock cycle, since the backward-looking window is constantly moving forward as the time elapses. In other words, if we want to look at the previous 10,000, so every time we have a new clock cycle, a new possible, it changed because the previous 10,000, or not a new clock, whatever, yeah, let's say a new clock cycle or a new reference.
Assuming that the reference happens every clock cycle.
Assuming that there's a reference every clock cycle, exactly. Let's assume with that. Assuming there's a reference every clock cycle, so now there's a new clock cycle. If I'm still looking at the old ones, I'm looking at 10,001. I'm skipping the one that just happened. So theoretically, at every moment, I would have to look at all the 10,000s. And that's going to be cumbersome to do that. So we're not going to do that. But theoretically, we would want to do that. That's the theoretical concept. When a page fault occurs, if there are no free frames, find the page not in the working set and evict it. In other words, if we still had a page lying around, in other words, we'll look at the 10,000 pages, at the 10,000 references, and we'll see that we have page 1, 2, and 3. But 4 is still in our window. It was still allocated to us because it used to be in our window. We'll get rid of it. You can even improve it, and you could say that we'll just look at 10,000 and we'll immediately remove him, even if there isn't a reference. We'll just say, remove 4. Why are we keeping him around? We haven't used him in 10,000 references. But you could say, no, let's wait. Maybe we're not going to do actual preemptive work to prevent possible crises. We'll just wait for the crisis to occur. A page fault occurs, now get rid of 4.
Otherwise, you might be doing this for work.
Yeah.
Well, we might know, there might be a
Small
good reason
size.
to do it. There might be a good reason to do it. What would the good reason be?
You don't have to.
You don't have to
check
remind
it every time. Like,
No, we still have to check every time. But we'll remove them, we'll preemptively remove them, because then we'll reduce the amount of pages that we're using, which frees up memory for other processes.
I understand, instead
That
of
could
having
be
to
good.
swap,
What?
instead of having to swap. Like, find which is the last.
Right, for some other guy, for some other poor guy who needs more pages, we should automatically reduce our usage as we see the need to, as we see the ability to reduce it. We see now that we've only been using 3 for ages. So let's get rid of the other 2 that we had. Get rid of them. And then somebody else can maybe hold them. Why hold up? Unless you're greedy and you just want to keep stuff, to yourself, because maybe you'll need it. Maybe you should release it so that some other process will have a possibility of using that frame. Okay, so when a page fault occurs, if there are no free frames, find a page not in the working set convicted. So WSSI, working set of processes, working set of process PI. In other words, every process has its working set, its theoretical working set. Total number of page reference in the most recent delta. Of course, it varies in time, as we said. The most recent delta, and we said its working set is a fixed number of page references. Wait a second, so look. Did I mention clock cycle? Yeah. Right. At every clock cycles, that's a mistake there. Anyway, whatever. It's by page, it's a fixed number of page references, not a fixed record of clock cycles. Sometimes we change it. We change it back and forth sometimes. Sometimes we use one. If delta is too small, so wait a second. The total sorry, back to here. The working set of processes. The working set of process PI is annotated as WSSI. It should be, well, I don't know why 2 S's, but
Also, the SI is the set. It's
working set.
So the SI is the set of process PI.
Working set set?
It's a set of the working set.
Working set.
No, it should just be working set. It's the working set for I. Anyway, I don't know why. That's the way I saw it. Total number of pages referenced in the most recent delta. Fine. If delta is too small, so wait a second. Now we're asking a different question. We said it's 10,000. We'll look back. Maybe we shouldn't look 10,000. Maybe we should look 100,000. Who decides? So we said like this. If 10,000 is too small, it will not encompass the entire locality. In other words, if we look back, we don't look back far enough, we might not realize that we've actually been using this page. And so, and if our delta is too large, we might encompass several localities. In other words, we don't even notice we've actually moved on and we're no longer in that neighborhood anymore. But our delta was so big, we're looking back at so much history that we think that we're including it in our set, even though it shouldn't be. So really, we want delta to be the right amount. If delta is infinity, then it will obviously be the whole program. We're just understanding what delta is. Now, D is equal to the sigma of all the sets. So D stands for demand. The total demand of frames by all, it should be of frame. Total demand of frames by all processes in the system is indicated by D, right? In other words, if the demand, which is equal to the sum of all the sets for all the processes. So that's how much demand there is right now. Right now, there's this amount of demand. And now we can say, if demand is greater than M, which is memory, then we have thrashing. This is just putting letters to symbolize what we're saying, but it's sort of obvious. If the total demand of all the working sets of all the processes is too big, then we're going to have thrashing. What do you mean too big? Bigger than memory. Policy. What? Demand is like the total need, let's say. Maybe it's need. The need for space, need for memory space. The computer has, let's say, 16 gigabytes of memory. If I take all the processes that are running and I say, what is their working set? This one requires 5 pages, this one 10, and I add them all up and I get more than 16 gigabytes, then my demand is greater than M. And then I can have thrashing.
The thrashing is only in locality.
So thrashing is what?
It's only if your locality is bigger than your.
No, thrashing is if your, if your locality,
Once in a while
if the set that I gave you does not encompass your working set, then this is thrashing. If the amount that I've allocated to you is not accurately reflecting your needs, your locality, your locality is your real locality. Your real locality, I didn't correctly assess your real locality, and I gave you too small of space for your locality.
The demand here is not the locality?
Demand here is the localities, but of all the sigma. Sigma means the sum of them.
Yeah.
So all the localities of all the programs, if their locality in reality is bigger, if all of them together is bigger than what I have, then there's no way to avoid it. I'm going to have thrashing. I can't avoid thrashing. Even if I figure out the perfect locality for everybody. Right?
Yeah.
There's a different problem that I made the locality. I didn't find the locality. I thought the locality was 3 pages, but it's really 4 pages. Then I'll have thrashing. So if I didn't get if that was what I was saying before, if I didn't get my delta right, my delta was too small, and I didn't capture in my delta the full locality, then I'll have thrashing for that, I'll have thrashing because that program doesn't have what it needs. But even if I theoretically got all the deltas right, I got the delta right for everybody, and I got their correct localities, but I add them all up, and it's not, and it's more than the amount of memory I have. Then forget. Okay, that's just okay. So now, how do we actually do this? So here's a kind of example, and we say like this. Imagine my delta is 10. Here it's 10. So if I'm at time 1, this is just time 1 and time 2 are not necessarily sequential. Like, in other words, this is just some other time. At certain time, my delta is here. So I can say my working set at time 1 is 1, 2, 5, 6, and 7. I don't need to count 7 many times. It's just that I count once. Whatever was in this range till that point, from there until there. So my working set is 5 pages. Now at time 2, my working set, well, I'm going to go again from 3 and 4, 3, 4, 4, 3, 4. So it's only 2. It's always 3 and 4. The minute I go at time 3, if I would go one more step, then now my locality would include 1 and 3 and 4. But at this exact point, my locality is 3 and 4. And you see here that there's a kind of, they're trying to write the numbers in a way that's kind of shows the locality. Because you see, I'm kind of in the area of the 7, 5, 1 area. And then I move over, I go to some 2, 3, whatever, 2, 3, 1, 4, 6 area. And then I go to the 4, 3. Right? There's a kind of, here I would go back to another locality. This 1, that's the moving van. Now I move to a new location. Now I went back. I'm kind of back in the same.
The ones who move you. Movers.
Sometimes when you change from one locality, let's say here the locality is 5, 7, and here the locality is 3, 4. But in order to get from 5, 7 to 3, 4, I had to go through, 6 and 2 and 1. I had to go some weird spaces, and then I finally got to that new locality. Sometimes they'll be in a kind of place that's not really well defined. Okay.
So does this mean that if we reference the same page many times, and hypothetically our working set could just be like a single page?
Yeah. It could be that if for the past 10,000 references, we've only referenced page 1, and our working set will be 1 page. Yeah. Why not? Okay, let's do, what is this? Example of working set. So if delta is 10, here, okay, this is the interesting part here. If delta is 10, we need to maintain 10 history bits to know which pages were referenced in the past 10 references. In other words, theoretically, we would have to have, if we would look back 10,000, we'd have to have 10,000 history bits. We have to know what were all the references in past 10,000 references. How are you going to know that? Keep track of it. You have to have a bit. So you have to have a bit for every page, whether it was a reference or not referenced. When was it? So this is here. So let's say we're not going to do an example of 10,000. We'll do an example of 10. So we have 10 bits. These are 10 bits. Okay. By the way, this is just like one implementation of it. There's many ways to do the concept you already got. The question is, how do we in programming actually implement it? So this is one way. The MSB, the most significant bit, which is this one, Yeah, represents, in other words, this column here. This is page 1, 2. These are all the pages. By every page, I have a bit. I have 10 bits, and the most significant one represents the most recently referenced page. So in other words, in time, at time t1, what's the most recently referenced page? 1. What's the second most recently page? 5. But let's just focus out at t1. At t1, we have a 1 here. Why do we have a 0 at all of these ones? Because at t1 they were not referenced. Now if we go to t2, at t2, what's referenced? 6. So if you look down here, I made it bold. There's a bold 1 here for 6 to indicate what 6 was. What happened to the 1 here? Well, it slided down to the right. See it there? It's still there. And all the zeros are still there. Now, at time 3, I put a bit back over here. I put a bit. Where am I going to put a bit? At time 3, 2. So here it is at 2. Page number 2, I put a 1. And the 1 for before at 6 is still there. And this one. And as I keep going, as I keep going, these ones keep getting moved down. Again, here, 1 at 3, at time 4, it's 3. This is time 4, and here is 3. And the 1 from here is here. And the 1 from here is moved down. Now you can ask me, what are these other numbers that I had over here? Where do they come from? Well, they come from time 0 and time -1, because if you look at time 0, it was 5, right? So here is a 1 out of 5. See that? So basically, if I look at any moment, I can I can determine what the working set is. The working set at time 1 is going to obviously include 1 because he was just referenced. It's also going to include 5, 7, 5, 1, 6, and 2. Well, that's what I have, but how do I have it? Because there's a 5, there's a 1 here and a 1 here. So he's going to be for sure in my working set. So 5 goes in my working set. 6 goes in my working set because he got a 1. But like 4 is all zeros. 4 is all zeros. So he was never referenced in time 1. There was no, in delta, given my delta, there was no. So you see how this works very logically. I'll have a bit for each. What determines the number of bits there? I have 10 because my delta is 10. I have that. That's not how else you do it. I got to keep track. I can't like look into the past. I don't have like a time machine. I have to keep track. I have to have bits to record the past so that I can know.
So this works with 10,000.
This wouldn't work with 10,000. You have to have 10,000 bits. It would be crazy.
Yeah.
But I'm just saying a theoretical way to do it for 10. It would work for 10.
And if you had a shortening, you know which ones within the 10 are the most recently, and not just the largest number. The largest number is the.
Oh yeah. If let's say the operating system came along and said to me, you can only have. No, they said the other way around. Which number should you replace? Which number should you kick out? The smallest number.
Yeah.
If I have to choose a victim, of these pages, say all these are in my memory, and the operating system says, sorry, you can't have all 7. You got to get rid of somebody. So I'll take the lowest number. Well, 0 is the lowest number, but there could be a place where, like over here, maybe I don't have a 0. So who will I choose? The lowest number of all of these, which will be what? This
7.
guy. Yeah, it'll be page 5.
No, 7.
7?
Yeah, it's 1 less than 5.
Oh yeah, it's 1 less. Okay, yeah, 7. Thank you. I just saw a lot of 1s. So I thought it was a big number.
Usually that's
7, yeah. So 7 I would get rid of. Not because he's because if he would be referenced, that would make him bigger. So again, yeah, but okay, so that's the basic idea. Yeah, this is something that I added actually to the material just to explain how it actually works. Now we're going to actually see a different version, but just before we get there, approximation of it. So that would be the actual working set. You understand what I mean? That would actually be knowing every single piece of information for the past 10 times. But we can also do an approximation of the working set. To determine the actual working set, since the set changes constantly, we need to check backward in time constantly. This is too costly. In other words, what I said here, the working set at time 1 and time 2 is not the same. So if I really want to know the correct working set at any moment, I have to check all the time. But we're not going to do that. Instead, we will check back at defined intervals using a clock timer to tell us when to check. So like every 10,000 seconds or every 10,000 cycles, we'll go back and check. So how we do that? We will thus check for every page reference for every page reference where delta is a time unit. In other words, we said before that delta was a number of page references in the past, 10, which means we only counted like how many times. We didn't do it every time changed, even though I wrote it like that, because we did it every time there was a new page reference. And now we're going to do it every time unit, because we're not going to keep track of every page reference in that way. Not a unit of page reference. Now we introduce a reference bit R for each frame. This bit is updated by the hardware at every page reference. So in other words, if in the past 10 minutes, this page was referenced, and that page was referenced, and the other page was referenced, then each of them will have their bit lit up. So now if I stop the situation and say, let's look who's been referenced since the last time I stopped, I'll see a 1 and a 1 and a 1 in these 4 pages. Now I'll wipe them out, and I'll let the clock run, and I'll go about my business, and I'll stop again. And I'll say, okay, since the last stop, who got a 1 set up? So I'll know who was referenced since I stopped last time.
Doesn't seem to keep track of the working set because you have to go back to take off.
Yeah, we will see. At every timer interrupt, this is what I just said. At every timer interrupt, the working set bits are right shifted, and the R bit that I have there is copied into the most significant bit in the working set bits. Then the R bit is cleared. The actual bit, the other bit is cleared, and to be for next time. And thus we keep track of which page is referenced since the last time we did it. How many? So well, let's see an example and go back. Here's an example. So let's say, what are we saying here? Delta is still 10, but our n is 2. What is n? Wait, working set with n bits, with 5 bits. Wait, I should actually read that. For myself at least. How many bits? We need n working set bits per page table entry. Right, for each page we need n bits. What is n? I didn't say what n means. This means that after delta divided by n times, there will be an interrupt every 2 times. In other words, in my case, if it's 5, then it'll be 10 divided by 5 is 2. For example, if we maintain 5 history bits and delta is 10 time units, then we need to have an interrupt. Then we need to have an interrupt 2 time units, every time 2 time units. If we wait 5 time units, then we would have extra and unused history bits. Yeah, I'll explain. The point is, in this case, look at this case scenario. It's basically like the previous one, except this is a 1 here. There's also a 1 here. Why is there a 1 here and a 1 here? Because at time 1, I look back 2. At 5 and 1. At time, notice I wrote time 3 here. I didn't stop at every time. I didn't stop like I did before. Every time I'll stop. I skip and I stop at time 3 now. But at time 3, I need to look at what has happened since my last time I stopped. Well, the last time I stopped was at time 1. What's happened since then is 6 and 2. So 6 and 2 will be lit up on the R bit for 6 and 2 will be lit up. I'm going to copy those into, here's 2 and here's 6 into the page. I'm copying, this is the R bit that I took from the page and copied it into this working set bit. And then at time 5, I look back and I see 4 and 3. So here's 4, here's 3 and 4. So where did I get them from? I copied them from the bit that was associated with each page. Why didn't I copy? Theoretically, well, I mean, the most I could get would be 2. The most I could get would be 2, right? If you could say to me, well, why don't you just, we could do it differently. What if I would stop instead of every 2 times, every 4 times? What would happen? Well, then at time 1, I wouldn't just copy 1 and 5. I would copy 1 and 5 and 7. And then I'd have more here. And then I would wait until time 5, and I'd copy 6, 2, 3, and 4. But then, how big would my window be? If I have 5 bits, each bit represents how much time in the past? 4. And I have 5 bits, so how big would my delta be? 20. You see what I'm saying? It would be 20. If my delta is 10 and my number of bits is 5, then I have to stop every 2 times. Because if I would stop every 4 times, then my delta would get bigger. Right? The delta would just by definition get bigger. So that's what I just wrote there. That delta divided by the number of bits equals how often to stop. And check. So why is this an approximation? Why is this not the same as what we did before? So pretty similar. Why is this called an approximation?
Well, you don't really store the order that they're.
Exactly. I don't know. Between 5 and 1, I don't know which one was first and last. So I don't really know. But I can still, right. So, right. Exactly. And I could actually have a tie here. If I wanted to choose a victim, I could actually have a tie. Could be that the 2 pages have the exact same references all throughout, and then I have the same numbers. So I couldn't actually choose a victim simply by choosing the lowest number. Remember, our purpose was to lower the overhead of maintaining history bits. Towards this end, we keep fewer history bits. But the drawback is now that our history will be inaccurate. It's somewhat inaccurate. Any changes in the working set will not be noticed until the timer interrupts us, and we check the reference bits and update the history bits. Right? This took me ages to figure out, by the way. To figure out that to get it into my head, that there's a reference bit and there's a history bits, and they're different. There's a reference bit associated with each page, and then we copy them into the history bits here.
Are they actually in different places too? Or we're just.
Yeah, they're different hardwares. This is going to be a register, of 5 bits. And there's going to be a register on each page. There's going to be a register to write every time there's a reference to light it up as 1. If it's already 1, just leave it as 1. But every time it gets referenced, it'll be made sure to be 1.
You can't just like repurpose the first bit, the most significant bit on the history and say that's reference. We just
So then you have 1 less bit. Right. Then you have 1 less bit here. It could be physically the same place. It could be different places. It doesn't matter. Right. Is there anything I missed here? How many bits do we need now? We need n. Okay, we said that. This means that delta divided by n time means there will be an interrupt. For example, we said this. We read all that, and we read all of this. So that's the approximation of working set. Did I talk about it anymore? Oh, I'll give it another. Wow, I've really going through this heavily. But I like this kind of stuff. I like algorithms, so I turned this course into algorithms course. But it really is. I mean, the truth is they teach working set. They teach something called. Wait, the second chance. In some of the courses, they teach something called this. I don't know if I do it. The second chance, the improved second chance. What? You saw that?
Just makes sense.
with multiple bits.
I forget it right now, but there's something called. We didn't. The second chance was before I didn't teach it. Second chance is like an improved second chance. Doesn't matter. Basically, you've got the idea of second chance. The truth is, we're done as far as working set, but. I mean, we could be done in a course theoretically in a university that taught working set. We did teach it, but I want to teach even more in depth because I can, and because I can. So selecting the victim in the working sets. We already said to just choose the number that's lower. As you can see in the previous slide, at time t5. Time t5. Who would we select, by the way? We would select 7 again, right? It should work. It happens to work out that it works out okay. It doesn't have to be that way. Like I said, there could be ties. It could be ties, but we couldn't get the absolute wrong one. I don't think we could have like a reverse case. Yeah. The worst thing we could have is a tie, but we couldn't have a case where the wrong one was selected. So as you can see in the previous slide, at time 5, our working set contains 7 frames. What if the process was given only 5 frames by the operating system? So in other words, we have 7 here, but what if we're only given 5? So we can't have that many. So which one should we have? we will select the victim page to be swapped out. This selection will be based on age. The page whose reference the least recently will be swapped out. And I don't know why I didn't write that, but it's the smallest number. We will need to maintain a last reference times up. So we could do it just the way you said with the number. I think I'm saying something different now. We will need to maintain a last reference timestamp for each page in the page table. Well, that's back to the other solution that we had. We need to be able to disregard the effects of context switching on. We need to be able to disregard the effects of context switching on processes. So we will need to maintain an internal virtual time and a virtual timestamp for each process stored in the PCB, the process control block. Virtual time, as opposed to real time, considers only the time the process was granted CPU access and not when it was switched out. In other words, we don't necessarily care about the actual time when this happened, when this page was used, but we care the time, the virtual time, the time for whenever I was alive. The process was frozen many times because of context switching. But if you ignore all that and just take the live time, I don't remember exactly why that's important. Some would always be the same. But whatever, we don't need the full time. We don't need the accurate time. We just need a virtual time.
Or you could go to a different processor then. If the CPU kept track of all this, then by going to a different process, then you'd lose all of your history.
No, I think I thought you were going to say something else. I was going to say if I'm choosing a victim from all the processes, then I don't care what you most recently used. I care because it could be you were out of the system for a while. I care who used it from when he was running the most recently. So then I need to be able to compare apples to apples. I need to have all the processes on the same slate. So therefore, I take real time out of the situation and just look at virtual time. At every timer interrupt, update process virtual time in the PCB and virtual time of reference page.
That makes sense.
At every timer interrupt, update process virtual time in the PCB and virtual time of reference page paging table entries. Did that make sense to you? I don't remember what I was thinking.
It's saying basically you have to update it each time the process comes back.
Right. Oh yeah. Okay. Exactly. At page P's age is the difference between the process's virtual time and the time of P's last reference. In other words, its current virtual time versus the last reference. And then I know how old that page is. Right? If I want to know how old the page is, I have to know my virtual time now and the virtual time of that page reference. At page fault time, assuming all pages are referenced in the working set history bits, the table is scanned and the entry with R equals 0, or if all entries are R equals 1, then the largest age is selected for victim, right? Somebody who hasn't been referenced at all, I'll get rid of, but somebody they're all referenced, then the largest age, the difference between the current time and his reference, if it's the largest, is going to be the one that's the oldest.
So we'll deallocate the resources of a process that's waiting, suspended?
No, of a page. We won't do, it could be of a process that's ready. If his is the old, well, I would just, What? How?
We'd have to go to him to see which ones
he's swapped. He's currently switched. He's currently off context switched out. We might be. I think we're thinking here about this particular. Wait, did I say the process? We're really thinking about one process. I was just explaining possibly why you want to use the virtual time. If it'd be only one process, then I don't see a difference why you would need a virtual time. Note that we could rely on the age alone and not use anyway. This page I don't think you have to know. Okay, this page I'm not going to make you know. But here, let's go. This is another implementation. I think this is a different. Oh no, this is maybe this is the idea. Here, current virtual time is 204 and to 204. So everybody is older than that. You see. Information about a page. This is the PCB. In other words, the PCB of this guy has got all kinds of information, but at some point it has information about one page. That's 2 blocks here. And I guess there's other information. But here I have, for example, where he is and where he is stored on the disk, for example. Anyway, here I have his last time he was referenced and the reference bit. What does this mean? There's a 0 here and the time. Why is there a 0 here?
Because there's not currently.
I take it back, and I tell you, you're not gonna have to remember that. You do have to remember because this is the same thing. You said at page filters, the table is scanned and the entry with 0 in his R is selected for the victim. So he's going to be the victim. He's also kind of the oldest. But this guy's also got a 0, but he's older. Page reference during this tick. This is the reference bit, information about a page. Okay. Scan all of the pages examining the R bit. If R equals 1, set the time of the last use to the current virtual time. You see that? Like this. If this is a 1 here, then that means at time, we stopped at time 2204. So now, this guy is going to be set to 2204 because it's a 1 here. And this guy's going to be, they're all going to be set to 2000. Anybody's got a 1 is going to be set to 2204. Right? Because he's been referenced and set the time last use to the current virtual time and then reset the R to 0. You see what I'm saying? We're going to set this bit to 0. Because this bit told us that since the last time we stopped everything and checked, since the last time we checked, he's been referenced. He's been referenced, but he hadn't been referenced. And this number tells me when he was referenced before the current time. But this bit, but in other words, I'm going to rewrite this. This number is going to be 2204. This is going to be 0. 2204 is 0. 2204 is 0. This one, well, he's not going to get, he doesn't get the right to be written 2204. Why not? Because he wasn't referenced at all. So he's going to still stay at his ancient time. And then this guy is going to be rewritten as 2204. 2204. 2204. And this guy wasn't also referenced. So now everybody's been referenced at this clock tick. Now, as time progresses, I'll again stop. And if these bits got lit up again, that means they were referenced since the last time. And then I'll write whatever new number I'm going to write here. Now, if I want to choose a victim, anybody who's got a 0, so for sure I'll choose him. If everybody was referenced, then I'll just choose, that means everyone's referenced recently, but I still got to choose somebody. I'll choose the one with the oldest number here.
We don't actually keep track of the history more than like our working set is just the time tick.
Right. In other words, however often we stop, then we record a new number there. We don't actually know the whole history. On the zeros, we'll know. If everybody would be 0, wait a second. Right, this is a kind of weird case that we have here. Because what this says is that he was referenced now, but before that, he was only referenced at this time. The question is, how often do we stop the clock? How often do we stop and write this number? I'm assuming that we do it at intervals, not all the time. So here, each entry contains at least 2 items of information. At least, because I'm saying this could be other information here. The approximate time the page was last used, and the reference bit. The empty white rectangle symbolizes the other fields not needed for this algorithm, such as the page frame number. Remember, the page table also tells me where the actual frame is. The protection bits, the modified bits, also the valid bit. Remember, it could be a dirty bit. It's been modified. I'm just wondering if we actually write this number, this 2032. We could, another way of doing it, the way I just said is one way. Another way of doing it is that you actually write it every time it's referenced. Every time it's referenced, you update it. That would be very slow. It would be totally inefficient. Because remember, the page table is not hardware. Okay, let's go on. Working set algorithm review. The hardware is assumed to set the R bits. Oh, we're gonna stop a minute here. Okay. Okay, so let's review the working set algorithm review. So the hardware is assumed to set the R and the M bits. So that's what we saw. In other words, over here, this is the R bit. And the M bit, we didn't mention it, the MEM is a modified bit, but that's obviously also going to be set. So notice every time there's a page reference, if it's a write, then it'll set the M bit and the R bit. If it's just a read, then it'll just set the R bit. Similarly, a periodic clock interrupt is assumed to cause the software to run. This is assumed to cause the software to run that clears the reference bits on every timer interrupt. So in other words, every time there's a reference, every time there's a timer interrupt, boom, we copy the current time into the time and we delete all of the reference bits because we don't need them anymore. We recorded the current time. The page table is scanned to look for a suitable, and also on every page fault, we try to evict somebody if we need to, because we have to, because it was a page fault. On every page fault, we evict somebody. The page fault could be, right, there's not at the same time as the clock time, as the clock stop. As each entry is processed, the R bit is examined. If it is a 1, the current virtual time is written to the time. So it sounds to me like we are, well, anyway, well, never mind. I don't know. Let's take it back. As each entry is processed, the R bit is examined. If it is 1, the current virtual time is written to the time of last use field in the page table, indicating that the page was in use at the time the fault occurred. So we're also copying, it's not just the time clock, it's also at every fault. It seems we're going to be copying, every time there's a fault, we're going to copy the time in. Since the page has been referenced since the previous time interrupt, it is clear, in other words, we may as well write it again. As long as we're there, we're going to write the new time. And then when there's a new page fault, well, we'll write it again, I guess. We'll write the new time. Indicating the page was used at the current time fault. Since the page has been referenced since the previous timer interrupt, it is clearly in the working set and is not a candidate for removal. Delta is assumed to span multiple timer interrupts. Right, our page delta, which is how far back we look to create our working set, is going to be bigger than the interrupt. It's going to take. If R is 0, the page has not been referenced since the previous timer interrupt and may be a candidate for removal. To see whether or not it should be removed, its age, that is the current virtual time minus the time of last use. So we have that current virtual time and then we recorded the time of last use, is computed and compared to delta. Compared to delta? If the age is greater than the delta, why would it be 0? And okay, fine. If the page is greater than the delta, the page is no longer in the working set. It is reclaimed and the new page loaded here. The scan continues updating the remaining entries, i.e. checking if the reference bit is 1, and so updating the time of last use. However, if R is 0, but the age is less than or equal to the delta, right? If R is 0, but the age is small, it hasn't been referenced, but it's small, the page is still in the working set. The page is temporarily spared, because it might be that everybody's in the working set. So the page is temporarily spared, but the page with the greatest age, smallest value of time last use, is noted. If the entire table is scanned without finding any candidate to evict, because nobody is not in the working set, that means that all the pages are in the working set. In that case, if 1 or more pages with R0 is found, the one with the greatest age is evicted. In the worst case, all pages have been referenced during the current clock tick and thus have an R of 1. So 1 is chosen at random for removal, preferably a clean page if 1 exists, with no M. Right? Yeah. In other words, if they're all in reference in the current delta, then we just choose one at random. And if they're all, unless there's some that are clean and some that are dirty, we'll choose the clean ones. Okay, page fault frequency, more direct approach than WSS. Remember, the whole point is to prevent thrashing. Yeah, go ahead.
Can I ask a question on the working set?
Yeah.
Moving forward, should we assume that working set it has a history or does not have a history then?
Well, no, there's there are two algorithms that are distinct.
Okay.
That's what I'm saying. There are two algorithms. Most of the people in the course are just shown this actually. And then I added this to explain how that's going to work in bits. I was like, okay, very nice, but how are you going to do that? So this is explaining how that works. Then, this is also shown, I think this is usually shown also. And then, which is like but they skip this stage.
Okay, so they do
This, yeah, and this as an additional algorithm that I'm adding to the material of the course. You have to know it all. You don't have to know. You don't have to.
The question was about like in the next at tick, I don't know, 15. Do I know what happened in tick 12? And if we keep the history, then
this is kind of like a history bit.
right. So, I mean, but the new one is not using the age would not show us.
Yeah, exactly. This is not a history. Exactly.
That's what I'm saying. So if a question asked about previous cycles, should we assume that there's history or not?
If I don't specify this algorithm, then assume it's this algorithm.
Okay.
This algorithm or this algorithm. I mean, right. If I just ask you in general, what is the working set algorithm, then all you really have to explain is this. This is the general algorithm. Just the fact that we have time, we look at the past, and that's it. How exactly? These are implementations. If I specifically mention the approximation, then it's either this is an approximation, and this is also an approximation. Because this I don't also have the full history, and this I also don't have the full history. Okay, so yeah, I don't. That's how I asked the question. I mean, I'm not gonna. I'll tell you one thing. I'm not gonna expect you to be able to reproduce this slide. This whole slide. I mean, you should know the algorithm, but maybe you're gonna skip something here. It's okay. I'm not gonna expect you to know this whole thing. But this, if I give you a picture like this, I might ask you what this is, or I might ask you to deal with this algorithm somewhere. All right, more direct approach than working set. I don't know what it does. Somebody on the phone look up what.
I think it's because the working set is the name, and then we're talking about the set of something. So it's set.
Okay. More direct approach than working set. I don't know. Then WSS establish acceptable page fault frequency rate. And use local replacement policy. I don't know what it means by local replacement. If actual rate is too low, process loses frames. If actual rate is too high, process gains frames. In other words, this is another way of doing it without any kind of algorithm. Just sort of keep track of the page fault rate for how frequently there are page faults. I mean, how are you going to keep track of that, actually? How are you going to keep track of the page fault rate? We don't discuss that either. How would you keep track of the page fault rate? Every time there's a page fault rate, you have a counter. And then at every, also delta. At every time unit, we'll stop. Remember, I'm confusing. Delta technically is not a time unit. It's technically originally in the theoretical algorithm. It's references. How many every 200 references, we look back. But we approximate 200. Instead of doing that, we use time sometimes. But I could have a time stamp here. Every not time stamp, but a time interval. Every 10 seconds. I stop and see how many page faults were there, and I have a counter that goes up. And if the count, every time there's a page fault, I increase I'd have to have a register where I add 1 to it, increment it every time there's a page fault. And then if I see that the page fault is above some predetermined threshold, then I say, oh, I better now that 10 seconds have passed, and I see that the rate is too high, I better give him another page. He's having too many page faults. Give him more pages so that he'll have more space and he'll have labels down, right? That's I think this one sounds very simple. Just keep track of page fault. It's on the page. It looks very nice. Just keep track of the page fault frequency, and then if it's having too many page faults, give it some more memory. If not, but you gotta implement that. You're gonna have to implement. Everything is implement has to be implemented. You can't just like say words. An operating system has to be programmed.
Could you take an average of like I don't know, when you would take like a snapshot of when we check the register, when we check the virtual time and the last time each was referenced, like the number of the time is varying. We can assume that each one is different faults or no?
What do you mean each one different fault?
Like when we have in the implementation of working set, we've got like 2084, 2003, 1980, 12, 13, things like that. Can we assume that each one of those, maybe if there are 4 distinct times, and we're either 4 distinct checks or 4 distinct faults?
I don't keep track of it. I don't understand.
In the 2 slides before,
Yeah.
we have lots of different numbers over there.
Oh, yeah.
If our delta is really big, then we can assume that each check was only at a page fault. So at the very least, there are the number of faults that are unique numbers.
Wait, I don't hear what you're saying. You're saying if a delta is very big, if we don't check very frequently, let's say we're very infrequently we check, then these numbers are going to reflect the time
The page fault occurred.
that not that this page fault occurred, but that another page fault occurred. And as I was going through, I was updating this guy
Right,
to
so
the current
it's a
time.
minimum number of page faults, because you could have 2 that were updated at the same time.
I don't know, what's the minimum number? This is a day. This is the time
Mhm.
at which there was a page fault, and I went through and noticed there was a 1 here, and so I just updated the number.
So that's like, so there are a finite number of unique numbers there, meaning there's a list of, like there's 19.
Well, if it's 1, 0, 1, 0, 1, 0, 1, 0, then I'll update this guy with the current number, and then this guy is a 0. I'll replace him, and
So the next time I will know that.
I'll change it, and this number now will be changed to the current time, and it's 1 for 1.
So in that kind of situation, I wouldn't have much information, but I would know that there were at least 2 faults. Because I'll have 2 distinct timestamps. In this situation, we have.
Yeah,
I don't
okay,
know,
maybe,
like
I don't
six-
know, I don't know,
six-
I don't know, you're making conclusions that are too confusing, yeah, I don't know, sorry. Okay, so let's go back to where we were. Working set and page fault rate. Page fault rate. What am I trying to say here? Oh, what is it saying? You guys tell me, I know what it's saying. What does this graph say? It says something, this graph.
Oh.
It's written there, but what does the graph mean?
That when the working set is analyzed, when it sees that there are more page fault, then it allocates more frames for the processes, and then the page fault rate falls. But it only sees, it has to go down, and then once it misses that spike.
Well, I mean, the truth is these dotted lines don't have to be exactly like that in the truth is ignore this line. What is it saying? Ignore the square. Ignore the square. What does it say?
We reached a whole bunch of files that
What?
looks like we reached a whole bunch of pages that we're not using anymore, from like a previous program, whatever, and we're moving them out and moving in new ones, and then we have smooth scaling once we have all current.
Right. No,
pages.
this is like the moving van.
Changing of locality.
This is the moving van. As we move, this is a we moved to a new locality. At the beginning of the move to the new locality, we're gonna have a lot of page faults because we're gonna be all the pages that we used to have are no longer good, and we need new pages. So I have a lot. But once we've gotten all the new pages loaded up, then we're gonna have very few page faults. We're in our locality, and then, but there's no guarantee that this is gonna coincide. I don't think there's any guarantee that this box that will dafka stop every time exactly at the right, I don't know, at the right moment or something. There's no way to know when these are going to occur. So this box, this superimposed box could be right in the middle here. Right? There's no, you see what I'm saying? There's no reason why that box should be exactly where it is there.
If it was just very flat, like we stayed in the same.
In fact, it's,
Yeah, at one point it wasn't.
in fact, it's not ideal. Well, ideal would be that this box would be over here. We'd rather have it go up here and across and down.
Yeah.
Because then at the very end, then we had a lot of page faults, and then we stop all of a sudden here, and we look back and we see, oh, we need to switch in new pages, and then we switch them in, and then we're here. Or wait. Oh, and maybe it does. Okay, I'm thinking about it again. Maybe what you're saying is right. Maybe you're saying like this: if we stop, I don't know, at a certain point, when do we identify that there were a lot of page faults? Well, we identify there's a lot of page faults, so then we switch them. I don't know that. I'm not sure exactly what it's trying to say, but the point is, the simplest point. I don't know what the working set part of it is, but the basic graph is showing you that there is this times when we have a lot of page faults, and that means that we are moving presumably to new pages, to a new page area, to a new locality. Our locality changing. That's all I see there. I don't know what the superimposition of that picture is. All right, that's enough for this. Let me stop recording.